Hello, dear students. Welcome back to our discussion on refrigeration and air conditioning. In the last session, we concluded, or we just understood that we studied about the standard vapor compression refrigeration system, and we understood that the pH diagram, pressure enthalpy diagram for the vapor compression refrigeration system is coming like this. Okay, so now let us in this session let us try to analyze the performance, how this standard VCRS is having its performance, or now let us try to analyze the various important performance factors of the standard VCRS. Okay, so performance factors means in the case of refrigerator, we have to find out what is the refrigeration effect, what is the work done during the compression process, then what is the heat rejected during the heat rejection process, like that. Okay, so now let us start one by one. So when we are discussing a refrigerator, our main focus, or our primary focus, will be on what is the refrigeration effect produced by that refrigerator. Okay, so in that case, now let us focus on our refrigeration step. Which is our refrigeration step? 4 to 1 is our refrigeration step. Okay, 4 to 1, it is a constant pressure heat absorption step. Okay, so refrigerant, while it is moving from 4 to 1, it is absorbing heat. Okay, so now let us focus on our 4 to 1 process. So so this is a pressure enthalpy diagram. So only here the main changes coming here in our diagram is the changes only happens for enthalpy and pressure. Okay, here that is the main focus. So we very easily we can apply our steady flow energy equation. That is, we are assuming that our refrigerant is flowing almost in a steady flow state throughout our refrigerator. Okay, then when we are we already have studied in our junior classes how to write the steady flow energy equation. So the same can be applied here in our refrigerator, in our various parts of our refrigerator also. Now let us apply the steady flow energy equation in our 4 to 1 process. Okay, so by applying steady flow energy equation to 4 to 1, how we can write it? H4 plus Q will be equal to H1 plus W, where H4 and H1 are representing the enthalpies of the enthalpy of the refrigerant. Okay, we are always talking about the working fluid here. Whatever energy equation we are writing here, we are writing it with respect to, or with reference to our working fluid, which is nothing but the refrigerant. Okay, so H4 and H1 are the enthalpies at 4 and 1. Then Q is the heat transfer, the net heat transfer happening during this process, and W is the net work transfer happening during this process. Okay, so when we closely observe this refrigeration step, which is nothing but a constant pressure heat absorption step. So this is there are no much moving parts or much work transfer involved in this 4 to 1 process. So we can take the net work transfer as 0. So what does that mean? What is the net heat transfer involved in 4 to 1? Which is nothing but Q41, which is nothing but H1 minus H4. Okay, and what is this net heat transfer happening during this 4 to 1 process? That is nothing but refrigeration effect. Okay, so now it is very easy. That is, we have very simply represented the refrigeration effect as H1 minus H4. That is the peculiarity, or that is the importance of a pressure enthalpy diagram. So whatever performance factor we require, we just need to find the difference between the enthalpies. So here itself you can understand the refrigeration effect during 4 to 1 process is nothing but H1 minus H4. That is, simply find out the enthalpies at the endpoints, that is H1 and H4, then simply find the difference between them, you can get the answer. So refrigeration effect is nothing but H1 minus H4, the difference between the enthalpies at the endpoints. Okay, then now let us move on to 1 to 2. That is, after coming out of the refrigerator or the evaporator or the freezer compartment, all these three terms are same. that is the freezer compartment or the refrigerator compartment or the evaporator compartment. All these three terms are denoting the same area. After coming out from this evaporator, the refrigerant is moving on moving towards the inside of the compressor, where the compressor will be compressing it during the isentropic compression process. So during the isentropic compression process, again let us apply the steady flow energy equation to 1 to 2. So that will be H1 plus Q will be equal to H2 plus W. Okay. So again here we can easily find out the values. This is a 1 to 2. What is that? It is a isentropic. Isentropic means a reversible adiabatic process. So it involves no heat transfer. So we can take the net heat transfer during 1 to 2 as 0, which leaves us with the work done, the net work transfer during 1 to 2 as H1 minus H2. Okay. So the net work transfer we have obtained as H1 minus H2, but we can observe H1 value is less than H2 value. So what does this mean? H1 minus H2 will be a negative value. Why this is coming as a negative value? Because here we are talking about work done by the compressor. The compressor will be requiring energy from us, or we are doing work on the system. Okay. So the work done on the system or work consumed from our side by the compressor, it is a negative term, because we are losing energy, or we are supplying energy to make the compressor work, which is a negative term. Okay. Actually, when will be the work transfer as when will we take the work transfer as positive? When a system supplies us the work. Okay. So here the system is using energy from us, so this is a negative term. In order to make it a positive term, in a mathematical sense, we are rewriting this as H2 minus H1. So the net work transfer during 1 to 2, mathematically it will be H2 minus H1, in order to just to make it a positive value. Okay. Thermodynamically it is a negative value. Now let us move on. After coming out from the compressor, the refrigerant is moving on towards the heat exchanger, or it will be passing through the heat exchanger, where it will be rejecting heat during the constant pressure heat rejection process. So 2-3, that is the process. So again applying the same steady flow energy equation through 2 to 3. So H2 plus Q will be equal to H3 plus W. So here also, if you are closely observing this heat rejection process, this is a simple heat exchanger process. There are no much work transfer involved. There are no much moving parts or anything else. This is a simple heat transfer process. So here we can take the work transfer as 0. So what is remaining? So the net heat transfer during 2 to 3, or the heat rejection, will be H3 minus H2. Okay. So H3 minus H2, here we can see H3 is a lesser value compared to H2. Okay. So H3 minus H2 will be thermodynamically negative. Why it is becoming negative? Because heat or energy is lost from the system. Okay. It is lost from the system to the surroundings. So it is a thermodynamically negative term. Just to make it mathematically positive, we can rewrite this heat transfer as H2 minus H3. So now H2 minus H3 will be the net heat rejected by the refrigerant when it is passing through 2 to 3, or when it is passing through the heat exchanger. Now let us again move on to the next important parameter, COP, coefficient of performance. So what is the how we can write the coefficient of performance of a refrigerator? That will be nothing but refrigeration effect divided by the net work transfer, or the net work transfer. Here it involves the net work transfer means what is the net work done by the compressor, because this during 3 to 4 it is a simple throttling valve. It doesn't involve much work transfer or energy. It is not a that much energy consuming device. The main energy consuming device in our refrigerator is our compressor. So the main work done will be the work done by the compressor. So we have already found out the work done by the compressor as H2 minus H1. Then also we have already found out the refrigeration effect as H1 minus H4. So we just need to substitute these values. So COP will be nothing but H1 minus H4 by H2 minus H1. Okay, so by simply looking at this pH diagram itself, we can write this. What will be the COP? Refrigeration effect. Refrigeration effect is nothing but 4 to 1 process. So H1 minus H4 divided by the net work done. Then work done will be the work done by the compressor, which will be H2 minus H1. So that will be the COP term will be H1 minus H4 divided by H2 minus H1. That is nothing but this relation. Okay. Then please note all these quantities have their units as kilojoules per kilogram. You should always remember this. Why? Because in all these relations we have not considered the mass flow rate of the refrigerant. Okay, actually this for example, in this relation refrigeration effect, actually if we know the mass flow rate of the refrigerant, we should have multiplied this H1 minus H4 by this mass flow rate of the refrigerant. For simplicity purpose, here in this analysis we are taking the mass flow rate of the refrigerant as 1. Okay, so that is why this all these quantities which we have just now discussed have their unit as kilojoules per kilogram. You always take care of the units. Then another important term is power per kilowatt of refrigeration. So in order to produce 1 kilowatt of refrigeration, what is the electrical power consumed by this refrigerator? That is the physical meaning of this term, power per kilowatt of refrigeration. So whenever we are designing, okay, so how we can find this power per kilowatt of refrigeration? That is how much energy, electrical energy is consumed by the refrigerator in order to provide 1 kilowatt of refrigeration. What will be that? It is simply work done by the compressor divided by the refrigeration effect. Okay, or it can be simply the inverse of our COP, that is 1 by COP. Okay, so actually this power, when we are designing a refrigerator as engineers, we should always keep this power per kilowatt of refrigeration as much as low value as possible. Okay, and we have to always keep the COP value as much as high value as possible. Okay, so that is the design part. So in the next session, let us do a simple problem on this standard VCRS. Thank you.